Hey YouTube, today we're going to talk about perhaps one of the most complicated topics in tuning large language models, RLfH, otherwise known as reinforcement learning with human feedback. Now, we're not going to get into the depths of the mathematics that power these because it is phenomenally complex and it would take hours to walk through. Rather, we're going to talk about the high-level concepts that make techniques like PPO and TRPO so powerful. And if you'd like to skip ahead to where we implement libraries to use these, feel free to skip to the chapter below. Otherwise, let's get into why these are so powerful and how they're implemented. Now, the majority of these reinforcement algorithms are doing what's called alignment, where we want our models to be as useful, accurate, and well-behaved as possible for interaction with our users. And this is especially important in generative models where they have the potential to generate very misleading or inappropriate responses that could potentially hurt our users or hurt the interaction with our users. And so we'd like to better align our behavior in our model with what we expect it to do. And so we achieve this through something called reinforcement learning, which is a training methodology that's based on rewarding desired behavior and punishing undesired ones. And there are some key concepts that we're going to get into a little more in the next slide, but this is state and observation space, also called our environment, our action space, our policy space, which is really just our weights, but we'll get into that a little bit later, our trajectory, or what are the steps that we took to get to an outcome, and then our actual reward function, which tells our model how well it did. Then we have derivatives, and these derivatives are just describing rates of change, and we need this to compute our gradients or the updates to our weights. And this is done through the Hessian, and if you'd like to learn more about this, we have a video that covers it in better depth on GPTQ. But basically what this does is it computes, and especially the inverse of this, computes our loss sensitivity if we update our weights. And so we can use this to make sure that the way we're updating our weights doesn't negatively impact our network's performance. And then we have our policy gradient, which is the reinforcement learning technique that updates our parameters so the network behaves more in the way that we would want it to. Now let's talk more about, in depth, these reinforcement learning concepts. Just as a disclaimer, this is a properly complex procedure or process, and it can take a little while to understand it. So I'm going to try and circle back and explain each component as well as I can. And we're going to loop back onto this example of us being at work and what a reward model may look like for us on a normal day. So what we have is an agent, in this case our model, that is learning and acting on our environment, where our environment is a state or observation space that provides reactions and changes the state that we're currently in. And these may have positive or negative rewards on us. And those rewards are what our model is looking to maximize through the actions that it takes, and those actions are what it can do in the environment. And our trajectory is the possible state and action combinations that we can take. So we could have combinations like state 1 and action 1 and state 2 and action 2 as we go through our states up here, for example. And now policy is probably one of the least well-explained concepts in reinforcement learning. And really all we're doing is updating the parameters or weights in our network, because those parameters or weights are what determine what our model is going to do. So if we want better alignment and we want better behavior out of our network, we have to update those weights. And so we have some techniques for doing that, but we'll get into that in a moment. Now, we also want to typically use something like a discount rate, where rewards further in the future or in further actions have less reward to them, because we want to get to the good actions as quickly as possible. And we can determine the goodness of things through a state action value function. And this determines for some policy, otherwise, again, our weights, how good is a particular action to take, and we can determine our updates from that. So if we look at this example, we start potentially here. So we've woken up and we have some choices that we can make. We can go to work or we can call in sick. Now, calling in sick has no cost, and going back to bed has a fairly high reward of 5. But if we can get to this promotion quickly, we get our highest reward of 50. So we have some possible actions that can change us into different states with giving us some reward. So going to work has a negative reward cost to it. But with our trajectories, where we can take multiple actions, we can see a little bit into the future, and we can know which trajectories give us the highest reward in the end. So if we can see this trajectory where we go to work, we work hard on a project, and then we ask for a promotion, yes, it has a high reward cost, but if we get there quickly, it has a high reward value. So depending on our discount rate and how quickly that's decaying, we would either go back to bed, because that may give us the highest reward, or we're going to aim for this promotion. And so there are some hyperparameters, namely what is our discount rate and how quickly can we update weights, that is going to determine how well we get into this state or ultimately this state. So now let's move on and talk about ways that we can apply this, namely through PPO or TRPO. So these alignment algorithms are either on policy or off policy. And what this means is either they're directly updating the network weights or perhaps they're updating some hyperparameters. But PPO and TRPO are policy driven. So we're directly updating the network's parameters to try and get better behavior. And to do this, we need a few functions. And there's a lot going on here, so we're going to just take this step by step and try to break down what each function is doing. So the first thing we have is our advantage function, which tells us for some trajectories, so some actions and states that we go through, we would have some maximum reward, minus or versus how advantageous for us is it to stay in a particular state. So a way to think about this would be on the previous example where we could get stuck perhaps sleeping or going for the promotion. So if staying in the sleep state is our most advantageous state, that's where we're going to end up. But if going down the promotion state is our most advantageous state, that's where we'd like to go. So there can also be states where either is preferable, and it could just depend on the day. So that ends up being a compromise state where we could potentially go down either trajectory. But to figure this out, we need to have what's called our objective function. And our objective function determines how are the rewards summed. This depends entirely on the algorithm, and PPO and TRPO are very different in this way. But since we're updating our network parameters, it's a function of those network parameters. But to figure out in at least TRPO, what is the maximum update that we can do, we need something called the KL divergence. And this KL divergence, all it tries to figure out is what is the difference between two probability distributions. So if we have probability distribution A and probability distribution B, how far apart are they, and how far do we need to move to get to them? So this gives us the idea of how much do we need to update our weights to go from probability space A to probability space B. But in TRPO, we want to combine this a little bit. So what we want to do is update the weights by taking the largest possible step on all of those weights, though constraining the update to be less than some value delta. And the reason we do this is because we're not looking at things in parameter space and big parameter updates. So if we change our weights too dramatically, we make our network unstable. Think about this like in GPTQ or some quantization technique where we're quantizing the weights. We're changing them in some way, and that can potentially harm the network. And the same thing can happen here. If I too dramatically change my weights to go from this probability distribution to this one, I could overfit into B. It could just prefer this state for everything, and you would have a less diverse network. So the objective function here that helps us do this is the expected value of taking a particular trajectory times its advantage. So what this really means is we have a sense for, given all of the trajectories, so all of the states and all of the actions that we could take times the advantage of taking that path, we know what each of the paths is like. And so we'd like to maximize this, right? We would like to take the highest advantage trajectory with the highest advantage function. And so the one thing that we're constraining, though, against is the update in the weights is some value less than this delta. So the delta is something we determine. We can choose to make it a very small delta. We can choose to make it a larger delta. Smaller deltas tend to result in better network performance. But computing this comes with a very heavy cost, because we have to compute the inverse Hessian or do line searches. And the inverse Hessian is the double derivative of the weight matrices, basically, where we're understanding the loss sensitivity for updating those weights. And so really all this is doing is saying, if I update this weight, I'm changing my loss potentially this much. So this is computationally very expensive and very difficult. So what we would like instead is to rely on an algorithm that doesn't have to do this, and that's what PPO does. And on the surface, PPO and TRPO are very similar, but PPO brings parameter space back into the equation, so it's looking at exactly how much it's updating the weights and clipping to a maximum weight update. And so this can allow us to entirely remove the KL divergence and rather consider, how do we maximize this objective function for some trajectory and some advantage clipped against a maximum update. So this is going to constrain the weight updates to a very small value, typically giving us a more stable network. Now, I know this was a lot to absorb. Really, all that matters in this is that TRPO and PPO are nudging the network's weights to the ideal behavior, because the policy, or what the network does, is determined by its weights. And so we have some data set that we've prepared that tells the network, I really want you to take this path. So learn or change your weights that make you prefer these groups of trajectories. And all those are actions, states. So the network takes an action, it gets into a state, it gets the highest reward. And TRPO and PPO approach it two different ways. TRPO wants to maximize against the distance between distributions. PPO wants to slowly nudge the networks towards those probability distributions. So now that we know what PPO and TRPO are, we can now implement them into our reinforcement learning from human feedback pipeline, which the process starts with an initially trained or fine-tuned model, just like we normally would, but then we're going to collect human feedback that measures the quality of the outputs from the model, where humans can evaluate and rank those outputs. And that can be done in a variety of ways. It could be numerical scores, or it could be sortings or orderings. but as long as it's something that we can use to help the model understand what's better. And that will then be put through our reinforcement learning, where we'll use something like PPO or TRPO. And then we will just iterate on this process. So the basic workflow is we would have our standard LLM. Then we would go and collect our human feedback. We would send that through our reinforcement learning, and we could repeat this process continuously. But this does have some pros and cons. And the advantages are, of course, improved performance. And if you want to see the difference that this can make, you can just compare Bing Chat versus GPT-4, where it doesn't appear that Bing Chat was trained with any kind of RLfH compared to GPT-4, which clearly was. And it makes a huge difference in that quality of performance. It also makes our model significantly more adaptable, where we can have subject matter experts guide the overall performance of a network towards, say, some specific knowledge domain or just general behavior. And then we can remove negative biases. Now, it's important to realize that the way like GPT-4 is very human in the way it speaks is a bias, but it's not a negative bias. We want to be able to use this to bias it towards good behavior and bias it away from negative behavior. And then, of course, we can continuously do this process. We can keep updating our network and get it to be more performant over time. And then most importantly, we get enhanced safety, where we know that the model, or have a better assurance that the model is going to behave well with our users. But it has two major disadvantages. The first being scalability, where this is an extremely expensive process. You have to pay people, lots of people to do this tagging, especially if they're subject matter experts like doctors or attorneys, are going to be hundreds of dollars per hour, and you need a team of them. And then, of course, subjectivity. What you or I find good is probably going to be slightly different, so we would rank things differently, and there has to be a way of dealing with this. But now we can move on to using a library that allows us to implement PPO. So this implementation of PPO, which will be in the description below, is a great example of how PPO should be implemented and how powerful it can be, and allows us to do some experimentation, specifically in this Google Colab, where we can run different parts of the PPO process and edit it to our heart's content and see what different hyperparameters and changes to the data sets do to our PPO. And I would highly recommend just trying some different configurations, and that's really the best way to learn this, is to see what your changes do and how they influence your results. And that's it. I understand. I promise you, I know this is very complex. It's difficult even, for professionals to implement this, which is why it takes so long to do this kind of process. But it is well worth the rewards because of how performant your network becomes. If this was helpful, please like and subscribe, and please let us know in the comments below what you'd like to hear about next. And please tune in next time when we're going to be walking through LLMs from start to finish and the entire process of how you get the completions. And then later next week, we'll also be talking about how to better set up validations for your fine tuning. And then later today, we'll be having our live stream on the same topic. So see y'all next time.